All right. Welcome and good morning. I'd like to introduce you guys to H.E.R.A.L.D, the hybrid exploration robot for air and land deployment. My name is Lauren Davis, and these are my teammates, Mike Kofron, Anthony Stroffolino, Stella, Latscha, and Gabrielle.
When we began this project, we looked at where robots might be able to make the most impact. In terms of search and rescue, robots have been edging their way into the field, and we believe that there's a lot of improvements that can be made as search and rescue robots. Here you see ground zero from 9/11, and you'll note that there are many thousands of rescue workers in this situation, but only 11 people rescued, and many people of the rescuers died because this situation is very hazardous for rescue workers. We sought to seek to make a new robot that might improve upon what's currently out there in research. Here you see some of our motivation. On the top are the research robots that we kind of based our robot on, and then down on the bottom you'll see commercial robots. Now all these robots are kind of tank-like, kind of shredded, a little bit bulky, and so we wanted to find a robot solution that might be a little bit more nimble, able to go under a rubble, able to find victims better than these kind of.
Our solution integrates both terrestrial and aerial robots in an effort to remove the shortcomings of each. Commonly, search and rescue efforts utilize a 4-inch boring tool to create a hole in a wall in which to insert a camera on either a telescoping pole or a robotic arm. Our mobile snake-like robot is a replacement for this technique in that it can actually enter the hole and then continue to move throughout a building. We also utilize a quadrotor for aerial surveillance. The H.E.R.A.L.D system involves 2 snake robots and 1 quadrotor. One of the interesting ways we can integrate these robots is by having the quadrotor dock on top of the snake robots and drive around like this. You're seeing that picture above, and we call it tank mode. This helps us to save battery life on the quadrotor because quadrotors are notorious for short battery life. We also have designed the quadrotor to be able to carry a single snake robot. This way, the snake can conquer obstacles that it can't on its own with the help of the quadrotor, and we can transport the entire system through the air to a new location.
Our basic system schematic is that we have a human operator using an Xbox or PlayStation controller. MATLAB then reads the joystick inputs from the controller and sends it to XP wireless radio. There's another XP on board, both the snake robots, that communicate serially with the Arduino microcontroller we have on board, and the Arduino additionally controls the motors and servos. We have 2 cameras on both snakes that are mounted on the rear that look forward, and one mounted on the front to look ahead of you. For the quadrotor, we have a similar setup, but instead of using an Xbox or PlayStation controller, we use an RC controller, which then communicates with the RD pilot, and the RD pilot sends PWM signals to 4 ESCs, which control 4 motors. Additionally, there are 2 cameras on board the quadrotor, one facing downwards to surveil the snake and any terrain below you, and one facing forwards to help control.
So our snake robot improves on current search and rescue land vehicles by being able to fit into small spaces, such as the 4-inch porthole that Mike previously mentioned. To reach this design, we went through many iterations. Due to the novelty of the system, we saw a lot of forces that were unexpected and also complex. To reach to the point where we had a stable system, we went through many prototypes in the early phases to reach the desired capabilities that we wanted. The snake also has 7 degrees of freedom, 3 in the wheeled segments that also have integrated treads, and also 4 servos. 2 of these servos allow the snake to move horizontally in the horizontal plane, which we call yaw, as well as the other 2 servos move in the vertical plane, which we call pitch. These 7 degrees of freedom allow us to maneuver in complex terrains as well as climb stairs. Also, we can maneuver in such a way that we can manipulate the center of gravity to recover from such actions such as tipping.
Because of the novel form factor of our snake, we had to custom make our electronics. So we went through many breadboard iterations to see which is the best combination to control all the motors and servos. And we decided that we should make our own PCB in order to better integrate with the snake. Additionally, because the servos require so much current to lift and maneuver the snake, we had to make a voltage regulation board in order to limit the current and not damage the servos.
On board each snake is an Arduino microcontroller running C++. The low-level embedded software on the microcontroller is all custom written, and it takes a serial packet with motor commands and translates these into actual motor commands on the snake. It gets the serial packets from a MATLAB instance running on a computer, which takes joystick input from a user on an Xbox controller, as we have on the table there, and translates it into a packet to send. The code is written in such a way that it's independent of the number of motors and servos on the snake, so that we could use this with any number of snake robots that have more segments than we do. Here we only have 2 or 3, depending on whether you want to call them the servos a segment or the wheels a segment. On the Quadrotor is an Ardu pilot. That's a board from Arduino, which runs open source software from DIY drones called Arducopter. It's basically a black box for us, allowing us to change only a few controller gates. Stella's going to talk about the Quadrotor.
So in terms of the Quadrotor, what we wanted, the metrics we wanted to design around were 4 main things. It had to be able to drive through a doorway. So it had to have a maximum footprint width of about 36 inches. It had to be able to carry a snake, so about a little more than 1,000 grams. It had to have 3 docking points, 2 on the outside and 1 in the middle, for tank mode and carry mode. And we wanted reasonable flight time, about 10 minutes with the snake and 20 minutes without the snake. In order to meet all these metrics, and to stay within a budget of $1,000, we couldn't purchase a Quadrotor that's currently available because they're very expensive, and they don't usually carry the amount of payload we wanted. We had to custom make pretty much all the parts. You'll see a custom designed 3D printed hub, as well as motor mounts and docking interfaces. Once we figured out the basic metrics for our design, we had to spend quite a long time searching through motors and propellers to find a very efficient combination because we need a lot of thrust. So here you can see power consumption for different sets of motors and propellers, and on the far right is the combination that we chose. It has the lowest power consumption for the given thrust. Once we had chosen our motors and propellers, we started to test the Ardu pilot. It had 2 high gains because it expects a lower weight and a lower weight Quadrotor than what we have. So you'll see some instability here from 2 large proportional gain. We had to tune those quite a bit, and once we lowered the gain significantly, we were able to get stable flight. So here you'll see H.E.R.A.L.D and R.S.L flying our Quadrotor, and we can get very good flight here out of our Quadrotor once the gain is working. Overall, our Quadrotor can carry quite a large payload for its weight, but it's not that far out of line with what's currently on the market. However, the total cost to produce this Quadrotor is much less than the cost is to purchase one. So here you can see our cost per gram payload is less than $1 compared to 10 for the nearest competitor.
All right, so the Quadrotor and the snakes are integrated using a series of magnetic docking phases. This passive, lightweight, and inexpensive system utilizes the high carrying force of the magnets and also the shear weakness. This is further increased by this alternating north and south configuration and the added space. We designed the docking faces to minimize any added weight to the Quadrotor. So the 2 carrying faces in the center, which are designed to carry the snake, obviously, can carry about 12.5 kilograms, but only require 5.5 kilogram centimeters of torque to undock, while our servo motors are capable of giving us 17 kilogram centimeters. The 2 outer faces, which are designed to maintain contact between the snake and the Quadrotor in tank mode, are lighter weight and can only carry about 8 kilograms while requiring 4 kilogram centimeters to undock. So quickly, to dock up, we drive up, actuate our servos at about 1.5 inches. They should snap into place, and then the snake can actuate however it needs to. From here, we can, take a short flight somewhere. And then to undock, we simply actuate our horizontal servos, and the magnets will disengage. They should. And then we can drive away. All right. So for our initial metrics, we actually looked at the National Institute of Standards and Technology, or the NIST Robo-Rescue competition. So we took a lot of their test course metrics to prove that our robot would be feasible in any search and rescue competition. Those are on your left in the table, but we decided to show you a few more in the video that you'll see to your right. So as previously mentioned by my colleagues, the use of a 4-inch boring tool is very common in search and rescue robots, and this 4-inch diameter PVC pipe can improve that metric for us. We also exceeded our goal of climbing a 15-degree incline and managed to climb this 32-degree cardboard ramp. Our snake is capable of traversing fairly aggressive terrain, and you'll notice that some of these rocks are as tall as, if not taller than, our snake robot. And finally, for one of our more exciting metrics, we were able to climb a set of stairs. This is particularly difficult for a robot as small as ours. And while these stairs are slightly larger than a standard staircase by a few inches, we believe that with some slight modifications, we should be able to climb over a standard staircase without problem. Also, this represents tipping and recovery.
Now we're going to show you a few videos of our integrated system as a whole. It is 3 operating modes. First is our separated mode. You can see here the 3 robots are operated independently. The left video is showing you a third-person view of the quadrotor flying over the snakes. And the right view is from an onboard camera on the quadrotor, demonstrating what it would be like to teleoperate this robot and its capabilities in aerial surveillance. Next we have tank mode. This is our main operating mode. In a second, you'll see the snakes drive up and dock to the quadrotor for tank mode. Then our operator is going to throw the controller into tank mode, which allows both snakes to be controlled from a single controller, as though it's one vehicle, which it is. And now he's going to drive around. Finally, we have our most exciting mode, carry mode. Here you'll see a quadrotor carry snake in flight. The snake's going to drive up to dock to it right now. And then you'll see the quadrotor take off. As you can see, this flight is relatively stable.
It's important to note here that we are flying at only about 40 to 50% thrust. So our efficiency testing, I guess, paid off.
And here you have the snake undocking and driving away, though it can't move very far on that block.
In terms of future research for this robot, so originally we set out to create a system that was novel in terms of the way it traveled through rubble and the way it might locate victims. We knew we were not going to implement this robot immediately on a search and rescue field, but we hope that this robot will continue to influence the research field in the future. There are some proposed projects at the top by PhD and master's students here at Penn in terms of improvements and uses for the robot system. One is quadrotor controller testing through the Protocol Program for Robot project at MIT. One is to integrate a low-cost laser scanner on the quadrotor to map rooms. And one is to add sensors for victim location onto the snakes and test that. In addition, our team would like to do some future work in the fall. A couple of us are master's students in robotics. And one of the big things we'd like to do is integrate more computer vision into the robots. We have a lot of cameras. And we didn't have time this year to implement a lot of computer vision algorithms, but we'd like to be able to autonomously track the snakes and as well as autonomously dock. With those improvements, we believe we could produce a publication at the 2014 IEEE International Conference on Robotics Automation. This is our goal. So we'd like to acknowledge the following people for helping us significantly in our project. They made a big difference that we couldn't have done that without them. And we'd like to open up the audience to questions.
I noticed when it lifted off that the snakes, the wheels kind of dropped down. Does it land okay with that? Or?
So what we can actually do is we can then actuate them back up so that it has room to land on the landing space.
Another quick question. What's the power consumption like? How long can these units go without returning?
In terms of the snakes, doing aggressive maneuvers, you can go around a little bit over half an hour. Then the quadrotor.
So for the quadrotor, it depends on whether you're carrying a snake or not. With the snake, you should be able to get about 10 minutes at least. Without a snake, about 25 minutes.
What is gain?
Oh, so the gains, with regards to the controller, there are gains of different, for example, we have an angular rate gain, which the gain is basically a number, a coefficient in front of the angular rate term in the controller, and amount of that coefficient tells you how much the autopilot will respond for a given motion. So if it's turning, for example, if it's rolling, the angular rate gain in roll will, if it's really high, it will increase the response if you send a control for it to roll. So like if you tell it to roll, if the gain is high, it'll roll more. So when we originally started, the gains were really high, so it responded kind of overcompensated for our motions. But once we lowered those gains, it kind of smoothed out a little bit. So that's what we mean by gain. So basically, just a measure.
Thank you very much.